Hello and welcome back to Calculus 1 on Saturday. So let's talk about 2.5 limits at infinity, which is different than infinite limits. So for infinite limits, the answer you were expecting was infinity, and that one was used to figure out the vertical asymptote. The goal for today is to talk about limits at infinity, which means that you go out infinitely far on x-axis and then look for the limit in terms of whether it's a finite or infinite value. So what we are doing now is best seen on exponential function. So I'm going to put exponential function graph. Whatever. A little bit stretched. Should have gone a little bit faster, but that's okay. Goes through 1, doesn't matter. And what I see here on this end is limit x approaches negative infinity. There is no a minus and a plus because a is a value. You are going to infinity. And in this case, the limit is 0 because you can see that this line is constantly falling down. So we're hoping that by the time it's at infinity, it will be 0. And then we have the other side, which is this blue side here, and that one would be limit x goes to positive infinity of f of x, and the answer is actually positive infinity in this case, because you can see that this one is going up to positive infinity as x on the x-axis, right, is going out to positive infinity as well. So this is what we are learning today. We are focusing on the situation that the limit as x goes to positive or negative infinity of some function f of x is either number or infinity. So this is our limit, and this is what we would say limits at infinity. And that's it. Now we can, so theory-wise, right, thinking about the concept, this lecture is over. But we want to also apply this, because just defining it for the sake of, having another math rule is not that important. We actually want to see a good use for this. And there are two good uses for it, both of which are studied again in Pre-Calc 1. And Pre-Calc 1 does much better job at teaching these two concepts than the vertical asymptote, where, right, we have seen that in some cases it was tricky, right? So the two concepts that you guys have regarding these are, if it's a number, it's going to be horizontal asymptote. And if you have infinities, we call it the end behavior of f of x, right, of the function. So both of these concepts you have covered in Pre-Calc 1, and they did a decent job. And since you only dealt with the polynomials and rational functions, you only learned one rule. Now you are learning the definition, which would apply to any function, even to those that you haven't learned yet, because once you learn the property of the function, you can use any function, right, regardless of whether you already learned the function or not. And so far, with all the exponential logarithmic trig and everything, you didn't even scratch the surface of functions. There is a book with 2,500 pages by Abramovich, which is called Mathematical Functions, and polynomials and everything you know so far fits on maybe 5 pages out of 2,500. So there's a lot of functions out there to learn, and obviously if you're interested. So the rules, when you learn a rule about the function, it applies to all of those 2,500 pages of that book, right? That's the thing. All right, so now let's talk about horizontal asymptotes. So we call it HA. So horizontal asymptote is a horizontal line where the limit, where the limit x goes to plus minus infinity of f of x equals L. Let's put this horizontal line y equals L, where, there we go, much better. So if you're, this should be red, much better. All right, so now we know what the horizontal asymptote is. Now, very important thing to know, I'm going to keep the red going here, is horizontal, let's do this way. F of x can go through horizontal asymptote. That's a very important thing. And then I'll just say horizontal asymptote, asymptote is there, must okay, let's flip it again. F of x must obey ha at plus minus infinity. There we go. Much better way to say that. So since these are the limits at infinity, we don't care what the function does locally, and the function can go through horizontal asymptote, and then eventually it will bend and follow the asymptote. So there are many functions that would do that. Eventually, in chapter 4, we are going to run into a function that is going to look like this. You're going to have your x and your y, then you're going to maybe have this one and this one, and then you will have the middle piece cut through like that. Notice that you have your vertical asymptotes, and then you also have your horizontal asymptote in blue. Now, horizontal asymptote, as you can see, in this case, the function cuts through the asymptote. It's possible. It's possible, but what this statement here said is that as you go to infinities on these two ends, the function will follow and follow the horizontal asymptote without crossing it or touching it into infinity. So that's the part that right, you have to. So both of these rules, right, are on the picture. The first rule is here, and the second rule is at the end. You might have remembered those rules. If the denominator has the bigger power and the numerator, you can, if you remember that, it's time to forget it now, right? Because now you can, that rule that you memorized, those three rules that you memorized in pre-calc, are only good for your horizontal asymptotes for rational functions. But they say nothing about exponential, trigonometric, or any other function, inverse trig. I mean, they say nothing about anything else, right? There were just three rules for the rational functions. But now, when you know the limit definition for the horizontal asymptote, you don't need to memorize those rules. All right, let's take a look at horizontal asymptote problems. By the way, if you have a question, you should ask, right? If you don't understand some concept, and also the chat on YouTube, so you can type stuff in there as well if you have a question. So, what is the horizontal asymptote for f of x equals 3x squared plus 6 divided by 5x squared minus 1? So some of you remember the rule from pre-calc, and you would say, oh, powers are the same, so just take the front coefficients and your horizontal asymptote is 3/5. And I just say perfect. Yes. If you know those rules for rational functions, you can use that rule and just say horizontal asymptote y equals 3/5, and you're done. So if you know the rule, you would say horizontal asymptote at y equals 3/5, and you're done. By the way, if you write this, I will mark it as wrong and hate you forever. So, I'm highly allergic to this. This is meaningless garbage statement. Never write this. Has nothing to do with anything. Horizontal asymptote is the horizontal line. And the line is x equals blah blah for vertical lines, and y equals blah blah for horizontal lines. So do not write that. All right. You trigger my allergies to people. How about that? So now, how do we solve this without remembering rules from pre-calc? Right? Well, we just take the limit. The definition clearly said, what is the horizontal asymptote definition? It says, take the limit as x goes to infinity and just solve the problem. So my job is to take this limit and solve this limit. The answer for this limit should come out to 3/5. Now, how do we solve this limit? What's the trick? The trick is to, when you have polynomials like this, which is technically your pre-calculus problem. So when you have polynomials, the trick is to divide by the x with the highest exponent. So that would be divide by x squared everywhere. And what happens then? Well, do the algebra, and x squared and x squared will cancel, so you just have 3 minus 6 over x squared divided by x squares cancel again, 5 minus 1 over x squared. And now you know that those properties of limits we learned last time say that you can apply limit to each one individually over here. And what you find is this creature of 6 divided by infinity and 1 divided by infinity. So how much is 6 divided by infinity? Well, what is division, right? Division is splitting the whole into parts, splitting a collection of objects into parts, or splitting one unit into smaller parts and you get fractions. So if I have, let's focus on limit 1 over x squared as x goes to infinity. It doesn't matter what number you put on top, but let's focus on the one from the denominator. So what happens as I cut 1 infinitely, right? If I am to plug in infinity, it would be 1 divided by infinity. Well, if I divide it by 2, it will have 2 pieces. So if I take 1 whole and divide it by 2, I would have 2 pieces, and the answer is 1/2, so smaller than what I started with. If I divide it by 4, you see the cut is still getting smaller. If I divide this by 8, you can see that each one of these pieces is even smaller. Divide by 16, we have 16 squares here. So your 1 whole is this big, and your 1/16 is this big. So you see that the more you cut, the smaller amount you get. Now this is something common sense. It's even used in the movie when, right, Joker kills the bus driver. And you know why, right? Because the cut that stays for one person is much larger than for 3, 4, 5, and so on. So, and yes, Paul, that's correct. So what happens is the more you cut, the smaller the pieces. So effectively, if you cut infinitely many times, you get a 0. So I hope this whole thing made sense. And now we can take this and we can write it here in blood. Limit x goes to positive or negative infinity of any number divided by x to any power bigger than 1 is going to be 0. I don't need this anymore. So now we see that this all matches, right? It all matches now. And what do I get here? I get 3 minus 0 over 5 minus 0, which is 3/5. So I don't need to have those rules memorized anymore. I can now solve the problem by remembering that if I have polynomials, I divide with the the exponent, right? The highest exponent in the problem. Let's see if we can find some spicier example in the book to look at. Ooh, okay. They have some awesome stuff over here. So, problem 47. You also have 45 to practice this beauty. Limit x goes to infinity of, it was kind of cool exam question, and now I ruined it. 2x cubed plus square root of 16x to the 6 plus 1. So the answer is clearly 2/3, right? By looking at it. How do I know? Well, square root of 6 is 4, 4 plus 2 is 6, 4 over 6 is 2/3 when you cancel. That's when you know what you're doing, right? But you would go, well, you can't take a square root of 16 because you have plus 1. Correct. Yes. And I can't cancel anything because I have plus 1 in the numerator. That's all true. The limits allow us to cut some corners. But let's see the proper solution here. Now, what is the highest exponent in the problem? and the highest exponent is 3. Now you might say, hold on, we have a 6. You don't. You have 6. You have a square root of x to the 6, and square root of x to the 6 is still 3. So highest exponent is cube for the entire problem. And then when you start dividing, when you divide the whole square root with a third degree, you will see when it gets into the root, it will become a 6. So let's go and copy this problem and leave some space now to divide everywhere. So I'm going to go 4x cubed plus 1, 2x cubed plus square root of 16x to the 6 plus 1. And now we divide everywhere by x cubed. Now clear some algebra. Please remember to write the limit all the way, every step, until you get to the last step. So now I have this limit here, and I have 4 plus 1 over x cubed divided by 2 plus, and now when this x cubed goes into the square root, this is 16x to the 6 plus 1 divided by x to the 6. So if you are stuffing things into the root, they pick up power. If you are taking them out of the root, the power reduces, right? So if you have 2x to the 4th in the root, then this becomes x squared root 2, because the 4 got cut into divided by 2, right? So it got cut by 2, and it comes out as the x squared. But now you can stuff this x squared back in, and it will pick up the 4th exponent. So if I stuff this cube inside a square root, it will be multiplied by 2, and it will become the 6 that we have over there. So now, with that witchcraft out of the way, we have limit x goes to infinity, 4 plus 1 over x cubed divided by 2 plus square root of 16 plus 1 over x to the 6. Now, what did we say for the limit of x to the p for any value, right? It's going to be 0. So the whole thing becomes 4 plus 0 divided by 2 plus square root of 16 plus 0, which is 2/3 as I promised. So you have problem 45 to practice. To some extent 44 and 46 are similar, as well as problem 49 with a little twist, and so on. I would like to work out one more of these examples before we jump to the last concept in this lecture, and that's problem 50. So these guys pop up as well, and then people lose their cool quickly. So x goes to, there we go, 4x, and then we have 3x minus square root of 9x squared plus 1. All right. Can you just plug in infinity and be done? Where you have, 4 times infinity is infinity. So infinity, open parenthesis, infinity minus another infinity. Like, what's going on? Technically, what you have here is infinity times infinity minus infinity. and how much is this? And you would say, well, infinity minus infinity is 0. Now 0 times infinity. No, it doesn't work that way, right? We can actually compute. And, it would be really funny if this is equal to like 2/3, like a previous problem. It would be interesting, right? So let's follow mathematics and see what this insane expression is equal to. And then you can go around and annoy others. Do you know that infinity times infinity minus infinity is equal to 2/3? Here, I'll show you how. So here, let's go. In order for me to solve this problem, I need to combine all of these things. And it seems to me that I should be able to somehow work out this square root over here to factor out x squared, which would become an x, which I can factor with this x here, and then that would go outside. So let's see what we get. X goes to infinity. The first thing I'm going to do is I'm going to factor out x squared. And when I factor out x squared, I get 9 plus 1 over x squared here. So when I factor out x squared out of 1, well, there is no x squared there, so I just put over x squared. Now, if you try to distribute this x squared, you will see that you get 9x squared, and then x squared and x squared will cancel, you will just get a 1. So this was all good, right? We're all done with this particular line. Now, I can kick this x squared outside, and it will become limit x goes to infinity, 4x, and now this becomes x over here, and we have this. I cannot take square root of 9 and x squared and so on because there is a minus in between. So that you cannot square root that. But what I can do is I can pull out an x now, which would make x squared on the other outside. So limit x goes to infinity, and I get 4x squared, and I get 3 minus square root of 9 minus 1 over x squared. And at this point, I can separate this into two limits using the properties of limits, which you might learned or skipped, I don't know. But we're going to separate these into two limits like this. And now you see that the second limit becomes 0, and the first limit is infinity. So this is working out to be 0 times infinity. And problems like this, again, will be studied in 4.7 when we do L'Hopital rule, because they require the derivative for us to solve the problem. So if you take a look at this, right, this piece over here will give infinity, and this piece over here will give 0, because this part goes to 0, and then you have 3 minus root 9, and 3 minus 3 is 0. So the way to solve these problems, as you are going to see, will be to put limit of 3 minus square root of 9 minus 1 over x squared divided by 1 over 4x squared. So we are changing this multiplication into this division, and I know, because I studied it right before and I now teach it, that this polynomial function should be the one to be flipped in the denominator, and you go from here to solve problems. So rest is in 4.7. We are going to solve this problem. I'm not sure why they put it here, but I just wanted to make sure that when, once you run into problems 48 and 50, and if there is something on the homework, you should definitely ask me to check if it's this situation. But you definitely have a problem that is not for this chapter. Maybe they just want you to get stuck. Then um, maybe you can use a software to solve this. Now, this is not that bad to solve. We just go through and take the derivatives and work it out. So it's not impossible. It's just that it takes a little bit long, and it's not for this lecture. We have one more concept of end behavior. And that is literally which way the function goes. So you can have the function go like this, right, on its end. So if you take a look at the parabola, you have combination of these two. If you take a look at the cubic function, you have combination of these two. Or this could be also your tangent function, whatever, right? If you take a look at the exponential function, well, then only this side is the upper right. Every function, unless it's constant, or it has the horizontal asymptote to follow, right, which is again going into flat, will have one of these infinities to go to. So this one is over here, limit x goes to positive infinity of f of x. It gives us positive infinity. And one on the bottom, as x goes to positive infinity, will give us negative infinity because it's going down into negative y infinity. Here is the limit x goes to negative infinity because this is negative infinity on x, right? So input f of x, and the answer is positive infinity because it's going up. And finally, limit of f of x as x goes to negative infinity will give us negative infinity. So that's the end behavior. And again, you studied this in pre-calc 1. They did not give you limits. They just said, oh, the function goes up and right and left and down and left and so on. But now you can pick up the function and figure out their end behavior by working out the limit. And you can either try plugging the numbers, or you can look at the graph. Many ways in which you can solve those limits. But if I am to go back to my exponential function, which was our first example, like this, we see that this end behavior here is the limit x goes to positive infinity of, let's say, e to the x is positive infinity. And that's the end behavior of the function. This side would be the horizontal asymptote, because the limit as x went to negative infinity of e to the x gave us 0. We started with this example to show both things, that both concepts which are given by the limits at infinity. There are no a and plus and a minus, right, approach from the left and the right, because these are infinities, not finite value a. So you are not approaching a point, you are approaching infinity. Now, these problems and these limits are very important, especially for differential equations and sciences and so on, because you want to, right, mathematics is used to predict the future, to compute the future, and so on. So when you have a mathematical model of some physical system, you want to make sure that that physical system is possible, right? That it's stable, it won't explode, and things like that. So when you find some kind of formula that is supposed to model physical reality, you can check that by taking the limit to see if the if it's plausible. So one of the good examples is the population model, which you guys learned and used in your pre-calc course. So population was given by P of t is equal to P0 e to the kt. So this was your population model that you use to compute the number of people or the number of rabbits or bacteria, doesn't matter, right? So if it multiplies, we can figure out the population if we know the values. Now, this type of model is good in the short run. So if you want to predict the population of humans within 20, 30 years, this model does the job, right? But if you want to predict the population of humans far in the future, right, presuming that all of the criteria of the world is not changing, so it's the current state. So you have the current birth rates and current mortality rates, and that's, you know, nothing changes. And yes, I know COVID is going on, but it did not add a significant amount of deaths. Certainly, if someone lost someone they know personally, right, that's a bad thing. But if you look at the population, the world population, and the number of deaths, COVID doesn't count at all as a pandemic in any of the previous plagues or something that used to wipe out like half of the population of the planet or something. That means every other person dies, right? In a room of 4 people, 2 are dead. Like that's something that counts. And the Black Plague, you know, from 1600s and even 1300s and so on. So those were the ones, right? This COVID doesn't count. So if we keep current birth rates and death rates and so on, you can see that this population model would not be possible at all, because when you take the limit of a model like this, in the end behavior, it goes to infinity, and you know that you cannot have infinitely many people on the on the planet of the Earth that has the finite surface area. You can't have infinite of anything other than infinitely stupid people, but that's not unit. It's finite amount of those units as well, like flat Earth, for instance. There's the one. Infinite stupidity. So when you take a look on the graph, right? And we're not going to go into negative time. We're just going to start with the population 0 there, which is when you started counting. And you have a graph like this, you see that the limit of your exponential function kt as time, right, because that's your independent variable, is going to shoot to infinite population, and that's not plausible, right, on the planet that has a finite surface area and resources and everything else. So we know it's a garbage model for the long run, which is why mathematicians sat down and thought hard and found the logistics model, which is the one that flattens after a certain time, and it approaches what we call the critical population, right, which is also known as carrying capacity of the planet, which is the value of the population that the planet can withstand with current, right, surface area, current resources that are available to be mined, and current energy production, pollution, and everything else that is there. So logistics model is the one that would have this horizontal asymptote. So you're still starting with your population, but then population never exceeds this carrying capacity, call it K. right? And it's still happening in time. They call it M. I mean, there are many ways. Now, this function is not covered here, so I'm not going to go into it. It's covered in Calc2, and then it's covered in details, including the derivation of it in differential equations. So you guys are going to see at least twice, those of you going to DiffyQ, obviously, you're going to see this logistic equation at least twice in your life. So I'm not going to take time now and explain those things because, again, we should focus on Calc1. So there's your lesson on 2.5 limits at infinity. You are looking for limit at infinity, meaning you are going to go into negative infinity or positive infinity, and then look for a finite value, finite number, in which case it's a horizontal asymptote. Or if you get in the infinities, it's the end behavior when we say the function either grows forever or decays forever. Now, there is another situation where the limit for these guys does not exist, and that's for, you guessed it, trig functions. Trig functions are outliers here because trig functions are periodic, they repeat. So as you are approaching infinity, they are still waves that go up and down, up and down, up and down, up and down. They do not settle to a one value, and they also don't shoot to infinity. So trig functions don't have a limit at infinity. So if you are doing this section 2.5 on trig functions, limit does not exist. So we can also add that here. So limit as x goes to positive or negative infinity of a trig function equals does not exist. Now, that doesn't hold for inverse trig functions. Inverse trig functions are just fine, right? So I'll put here not for inverse trig, not for inverse trig, because inverse trig, let's say y equal inverse tangent, that has the horizontal asymptotes, so it works just fine, right? So if you say limit x goes to infinity of tangent inverse of x is equal to pi over 2. If you learned the graph in this graph will be useful a lot in Calc2 and differential equations. We might see it once or twice in Calc1, but you will see it much more often in those courses. You should know that the graph looks like this. And there's your pi over 2 and negative pi over 2. And you see that the x goes to positive infinity is pi over 2. So that's a horizontal asymptote. And as it goes to the left, to the negative infinity, it will be negative pi over 2 on this. And that's it. That's the story of this 2.5 limits at infinity. We are going to restart the stream and talk about continuity in 2.6.